Tinder feels so simple, doesn't it? Swipe left, swipe right. But behind that super simple flick of a thumb, there is a massive, massive engineering machine. So today, we're going to peel back the layers and see what it really takes to build an app that literally changed how millions of people meet.
And that brings us right to the heart of the challenge. I mean, how do you even begin to design a system that can handle over 1 billion swipes every single day without completely falling over? It's a question of almost unimaginable scale. 1 billion. Just let that number sink in for a second. That's not per month or even per week. That is the daily reality for Tinder's engineers. This single number is exactly why the tech behind this app is so fascinating. And it's pretty much where our whole story begins.
So how do you even start to tackle a problem of that size? Well, it's kind of like building a skyscraper, right? You don't just show up and start laying bricks. No, you start with a blueprint. And in the world of software, that blueprint is all about defining your requirements. Now, engineers split this blueprint into two really distinct parts. First up, you've got your functional requirements. That's just what the app does. Swiping, setting your preferences, the stuff you see. But then you have the non-functional requirements. And this is the crucial part. It's how well the app does all that stuff. This is where the real engineering puzzles are hidden. For an app like Tinder, this whole thing really boils down to 3 key puzzles. First, low latency. The app has to feel lightning fast. Second, high throughput. It has to handle that flood of 1 billion swipes. And third, swipe consistency. It absolutely, positively cannot afford to miss a potential match. So let's dive into how they actually solve them. Okay, so let's tackle our first puzzle. And it starts the very moment you open the app. You just expect to see potential matches, like now. That need for speed, or what engineers call low latency, is the first huge challenge. Think about it from your perspective. You open Tinder, you want to see profiles immediately. The goal for engineers is to make that happen in under 300 milliseconds. That's literally faster than your brain can even register a delay. But here's the catch. Finding people based on their physical location is surprisingly difficult to do that quickly. And here's why it's so tough. A standard database is awesome for simple things, like finding a user by their name. But location isn't one piece of data. It's 2-dimensional, latitude and longitude. Asking a normal database to find everyone near you is like asking a librarian to find every blue book in the library, but they don't have a card catalog. They'd have to physically scan every single shelf, which would be incredibly slow. So what this means is they need a completely different kind of tool. And the solution is this really clever specialized thing called a geospatial index. You can think of it as a custom-built map made just for location data. When your app asks for matches, the system doesn't scan everything. Nope, it just glances at this special map, which instantly points to who's nearby and delivers that stack of profiles in milliseconds. Problem solved. All right, on to puzzle number 2. This one happens at maybe the most exciting moment for any user. That split second, you swipe right and you think, is it a match? This is what we'll call the instant match problem. So picture this. What happens when user A swipes right on user B, and just 5 milliseconds later, user B swipes right on user A? In the real world, that's a match. But in a massive distributed system, those 5 milliseconds are an eternity where things can go horribly wrong. This is a classic race condition. This entire problem comes down to one single powerful word: consistency. In a database, consistency is the guarantee that every time you ask for information, you are getting the absolute latest, most accurate data available. Without strong consistency, when user B swipes, the system might not have even seen user A's swipe yet. And poof, that potential match is just lost forever. Now, there's no one right way to solve this. It's all about making trade-offs. One option is a background job that just cleans up mismatches later. A much faster solution uses a high-speed cache, something like Redis, to check for both swipes at the exact same moment. Or you could go all out and use a powerful database like PostgreSQL that's built to handle this perfectly. But it might be way more expensive to run at Tinder's crazy scale. Every single path has its own pros and cons. And that brings us to our final puzzle, which is honestly the biggest one of all. How in the world do you survive the sheer flood of data that's created by all that swiping, every single second of the day? At its peak, Tinder has to handle up to 100,000 swipes per second. That is not a typo. 100,000 new pieces of information that have to be recorded reliably every single second during those busy hours. It's just wild. In engineering speak, this is what's known as a high write throughput problem.
It's kind of like trying to be a court stenographer in a room where 100,000 people are shouting at you all at once. How do you possibly write everything down without falling hopelessly behind?
And once again, the solution is all about choosing the right tool for the job. See, a general-purpose database is like a detailed notebook. To add something, you have to find the right page, find the right line, and then update it. It's precise, but it's slow. But a right-optimized database like Cassandra works differently. It's like just adding a new sticky note to the very end of the book, no searching required. You just append the new info, which is dramatically faster and absolutely perfect for handling that insane flood of swipes. So after looking at how they tackle speed, consistency, and this incredible scale, what's the big takeaway here? Well, the core lesson of designing any system this massive isn't about finding one perfect answer. It's about something a little more nuanced.
And it all comes down to this idea. Great engineering isn't about finding a single magic bullet solution. It's about the art of the trade-off. It's about understanding the problem so deeply that you can make really smart choices between different and often competing priorities.
And we've seen these trade-offs in action through this whole explainer. Do you prioritize raw speed, or do you have to keep your costs under control? Is perfect up to the second consistency more important than making sure the app stays online no matter what? Is a simple solution better than a really complex one that performs just a little bit better? These are the tough questions that engineers have to balance every single day.
And this really brings us to our final thought. The next time you open an app and it just works, whether you're ordering food, getting a ride, or, yes, swiping right, just take a second to think about the incredible engineering that's happening just beneath the surface. What hidden complexities are making that seamless experience even possible?